Hi, this is Todd Stone, Director of Client Services for True North Outdoor, and I'm here with Bill Nolde, our staff agronomist. We're going to be talking today about our landscaping diagnostics. We get a lot of questions about the diagnostic reports that we actually provide our clients, so we thought we'd take a little bit of time here to explain what the different things are on both the soil analysis that we do as well as the plant leaf tissue analysis. Bill, we're just going to go ahead and we're just going to kind of highlight different parts of this soil analysis report and just take a moment and kind of explain the importance or lack of importance. Some of these aren't as important as others. And we're just going to start on the left-hand side with organic matter, and then we'll work our way to the right and then down. So starting with organic matter, tell us about that.
When a soil testing laboratory gets a soil sample, they have a whole host of different methods that they can use to extract the data that someone might be interested in reviewing. One of those first things is organic matter. By the way, what you're going to be seeing here are the extraction processes were done by wet chemistry analysis, which is the most common method that's used at testing laboratories. And organic matter is plant organic matter, in other words, dead or dying roots, root hairs, certainly microorganisms, live or dead microorganisms, macroorganisms such as earthworms or nematodes, bill bugs. Any creature that lives in the soil can become organic matter, just like any plant. Root matter can be considered organic matter. And these are in varying stages of decomposition as well. And so the soil testing laboratory can identify these and typically will send a target range. And on this particular test, we see an H by it. That means it's on the high side of the typical range, which is 2 to 4%. This is a percentage of the volume of the soil sentence. So 3.7% is organic matter. Organic matter is particularly good, but if it's on the high side, or we see a lot of times very high, to me that's an indication that soil microorganism populations are being suppressed and have not decomposed this organic matter rapidly enough to stay within that target range of 2 to 4%.
Okay. Phosphorus.
Phosphorus, there's 3 extraction processes that are available to this laboratory. They chose to do 2. One was on the very low side of the spectrum. The other was medium. When you look at this test, you look at it as a whole. In other words, you'd like to see sufficient or medium throughout all of the tests that are done, and you kind of take an average of the two. So I'd say these are on the low side of the sufficient medium range. Phosphorus is interesting because it's very immobile in soil. It attaches itself to other elements in the soil, calcium in particular, and you get calcium phosphate, and it tends to stay put, does not dissolve in water very readily. So the secret is if you have a very low or low phosphorus level, that should tell you your plant material is not being supplied enough phosphorus, which is necessary for root development, in order to sufficiently replace the root mass that is dying or has been sloughed off. So it's something to pay attention to.
What does phosphorus do in plants?
It's necessary and responsible for root mass generation.
Okay. So potassium.
Potassium is just the opposite of phosphorus. It's very mobile in the soil because it's very soluble in water. As we look at these elements, we should also think of these as single ions. In the case of phosphorus, it's actually phosphate, which is an anion, but most of the nutrient elements are cations, they're positively charged, and potassium is one of those, but it only has one positive charge, so it's kind of a weak cation, which is why it's very soluble in water. It can be plucked off a soil cation exchange site very easily and then leached past the root zone, and it becomes unavailable for the plant to use. In general, potassium is necessary for overall plant health. It helps plants to resist diseases. So it's kind of all around everyday vitamin for plants.
Magnesium.
Magnesium is an interesting element mainly because it's not normally considered to be part of a fertilizer, if you will. Magnesium is very essential. It's one of the macronutrients in fertility management because it is the core of the chlorophyll molecule. A lot of people think nitrogen makes plants green. Not true. Magnesium makes plants green.
Okay.
Magnesium is the core of the chlorophyll molecule, and all the other ions attach itself to magnesium. So without magnesium, I don't care how much nitrogen you put on, it's not going to make that plant green.
We see on this one that it's very high. I know some things when they're very high, it's a big deal. Some things it doesn't really affect the plant that much. Are there any implications with very high?
Not really. This is why it's important to combine a soil analysis with a plant leaf tissue analysis.
Okay.
If we look at a leaf analysis and it shows a low magnesium level,
Mm-hmm.
that means that this magnesium is tied up in the soil matrix and basically is unavailable to the plant. It can't absorb it, so it's just sitting there immobile.
Okay.
And so we have to do something to condition the soil to make it available.
Okay. So calcium, what does that do?
Calcium, in my professional opinion, is, if not the most important, certainly in the top two important plant nutrient elements. It is essential for cell wall structure. It is the core nutrient element around which all the other molecules attach themselves to create a cell wall. Without good cell wall structure, plants will collapse. They're susceptible to root rot and insect attack very easily. It's been known that good levels of calcium in plant leaf tissue can effectively resist chewing insects. So the
Okay.
more calcium you have, the less insect attacks you're going to have.
Okay. Sodium.
Sodium is the one element in a soil report or a leaf tissue report that is not truly a plant nutritional element. It's everywhere, very present. In this particular case, it's in the moderate level. The reason it's on this report is we want to know whether or not the sodium level in the soil is going to present a hazard to plant nutrition, because it's very mobile in soil. It's always in soil solution. As a matter of fact, the vast majority of sodium in soil is delivered by the irrigation water, and then it tends to accumulate. So it depends on how well the soil drains. If it drains well, you're going to be able to leach all of that sodium past the root zone. But if it does not drain well, then it becomes very toxic to the plant, and many plants have died from sodium toxicity.
Okay. Of course, we all have heard of pH in our high school chemistry class, but what does it matter as it relates to soil?
Okay, let's define pH first of all. The P in pH stands for potential. The H is hydrogen. The potential hydrogen is a logarithmic evaluation of the acidity or alkalinity of a soil. 7 is neutral. Anything over 7, in this case 7.5, is slightly alkaline. Many plants will do just fine in soils of pH 7.5. If you were to ask me what's the perfect soil pH, it would be between 6 and 6.5, because that's on the acidic side.
Acidic.
Slightly acidic, because most of, when we talk about the micronutrients, you'll find most of them are metallic cations, and they need to be in an acidic solution in order to dissolve and become plant available.
Okay. Cation exchange capacity.
Yeah, this is a calculated figure also, and what it is, it's an evaluation or estimation of the ability of the soil to exchange these nutrient cations with one another so that they become available in the soil solution water to be absorbed by plants. All plant roots are not like straws. They don't suck up water and nutrients. All nutrients and water move through a cell wall by osmosis. So you have to have a large amount of these cations, if you will, in other words, the positively charged nutrient elements, to be able to push this chemical reaction in the direction you want it to go, which is to have the osmotic potential, which gets back to pH again, to move toward being absorbed through the plant leaf or plant root tissue by osmosis. One thing that you can look at 18.2 CEC level is that the higher that number, the closer you get to having clay soil. Kind of around 18 to 20 is indicative of clay soil. Over 20 is you definitely have a silty clay soil, which makes it much more difficult to grow good quality plants. 18.2 is okay. I would prefer to see it 12 to 15.
Okay. All right, so this is kind of a mouthful. Percent-based saturation.
Percent-based saturation is a computed calculation originally designed and presented to the agricultural community by Dr. William Albrecht from the University of Missouri. And this is a very helpful set of criteria which compares the relative percentages of potassium, magnesium, calcium, and hydrogen. And then, of course, for good measure, sodium. Sodium's the bad actor in this group. All the others are good. There are specific numbers. For example, potassium we like to see between 2 and 6. It's a little low in this particular case. Magnesium, 15.7, usually between 10 and 18 is good for that. Calcium, anywhere from 60 to 80, 85 is a good number, and it's right there on this. Percent of hydrogen has a 0, and it will always have a 0 if the pH is over 7.0. We begin to see a number there when it's below 7.0. And the sodium is a 1.9. A 0 would be ideal. Anywhere between, I've seen as high as 6. It depends on the extraction process, but on what chemistry. You want to see about a 0.5. Anything above that, and chances are you're going to have a sodium problem in the soil.
Okay. So the next thing, we're going down here and look at nitrate, and I know you told me that wasn't very important. Maybe you should elaborate on that.
It's on the soil test report because they can do the extraction process for us. It's easy for them to do. So something else for them to throw on here. The reason I don't really pay much attention to it is because it's so variable. Nitrates are very soluble in water, then they're used by the plants. So
would that be nitrogen if in the
nitrogen.
way we're thinking about it as
Yes.
common people?
Yeah, that's the nitrogen part of the fertilizer. Nitrate is the most common. Ammoniacal is another version of it. So it's either ammoniacal nitrogen or nitrate nitrogen.
Okay. All right, so now we get on to, these are the micronutrients, is that right?
These are the micronutrients. Sulfur is used a little bit more than the others, and you'll see on the report, VH is very high, M is moderate, L is low. So we look at these as a whole, but sulfur, zinc, manganese, iron, copper, boron are micronutrients because they're only used in very small amounts in order to be useful in a plant. It does not mean that they're not important, because if you have any one of these that are low, it is what's called a limiting factor. And if you have too many that are low, you will get poor plant response. And each one has a metabolic process. I won't go into each one, but one that most people are familiar with, sulfur, for example, is helpful in the good range of suppressing diseases, plant diseases. But the one that most people focus on is iron. There's a thing called luxury consumption of iron. It attaches so readily to the magnesium ion that you can actually stimulate the greenness of plants. So you can add luxury consumption of iron and turn turf grass, for example, extremely dark, almost iridescent green, if you want to do that. And its molecule is such that it will enter the foliar part of a plant, the leaf part of a plant, very easily, especially if it's chelated, and absorbed within 24 hours, you'll get a deep, dark green. So it's an element that landscapers and horticulturists can use to foliar feed a plant and get a very, very fast response. And it's very pleasing to the eye. Sometimes it's short-lived, but for a special function, it's a great way to get a nice dark green color without adding additional growth.
Does it matter in this case? It says the iron is very high. It says
Yeah.
the sulfur is very high. Is there danger in any of the micronutrients being at very high levels, generally speaking?
Yeah, sometimes iron will be absorbed at the expense of something else. In this particular case, I would say manganese and boron are being kind of shoved out of the way because iron is a preferred nutrient as far as plants concerned.
Okay.
It could also be in soil that there just hasn't been any manganese or boron added. You got to remember, most granular fertilizers, the vast majority, do not have additional micronutrients in them. Some will add, well, for example, sulfur-coated urea. You get lots of sulfur from that, and you can add iron. But the others, you'd be hard-pressed to find any fertilizer over the counter that adds zinc, manganese, copper, or boron in it.
Okay. We'll just skip copper and boron here, and then this little one here, excess lime rate, is that important?
Not usually. In most parts of the country, acidic soils are not seen nearly as much as alkaline soils. But if you have acidic soils, it's going to be very obvious because your pH will be below 7. And if it's much below 7, then there'll be a need for adding lime. Lime will raise soil pH. It's very easy to raise soil pH. It's very difficult to lower it.
Okay. Last one, soluble salts. Is that important at all?
It's something to look at. Soluble salts can be a whole host of different things. But what's being measured here is the soluble salts that are easily extracted off the soil particle. And in this particular case, most of these salts, as a matter of fact, all fertilizer elements are salts. By their very nature, they have to be in order to be solubilized and be absorbed by a plant. So what that tells me is most of the nutrient elements that you see in this test are locked up and bound in the soil, okay,
Okay.
and are plant unavailable because
So
we
in
have
other
low
words,
soluble.
all those nutrients are there, but they're not being soluble.
That's
So your
right.
plant can't get them. Right.